Imagine a universe entirely frozen in place. No motion, no heat, no change. Without energy, absolutely nothing happens. In physics, energy is a measurable quantity that describes the capacity to cause action, do work, or produce heat. It is the stamina meter that dictates exactly how much a system can do. To track this invisible currency, physicists rely on a conceptual tool called a system boundary. This is an imaginary line drawn around a specific object. Everything inside is our system, and everything outside is the environment. This boundary allows us to see exactly when energy enters or leaves the area we are studying. Without defining this boundary, tracking energy is like trying to balance a budget without knowing which bank accounts actually belong to you. Now, imagine you walk up to a massive concrete wall and push against it with all your might for 3 unbroken hours. By the end, you are sweating and your muscles are burning from the exertion. Curious tone. Has any work been done on the wall? In physics, the answer is a hard no. In the scientific sense, work isn't measured by how much you suffer or how tired you feel. It is defined by the physical movement your effort actually creates. Work is the primary mechanism for transferring energy into or out of a system. This transfer requires 2 things: a force, like a push or pull, and displacement, the distance the object actually moves. This explains why the wall doesn't count. Because the wall stayed still, the displacement was 0. No energy was transferred to the wall, so no work was performed. This diagram shows the relationship in action. To calculate work, we multiply force by displacement. Both work and energy are measured in standard units called joules. If a student applies a constant force of 45 newtons to push a cart a distance of 12 meters, the calculation is simple. 45 times 12 gives us a total of 540 joules of energy transferred to the cart. Work is strictly the successful transfer of energy from one object to another, regardless of how hard it felt to accomplish. But there is a second layer to this. Consider walking up a flight of stairs versus sprinting up that exact same flight. The total work done in both cases is identical. You are moving the same weight against gravity over the same vertical distance, yet sprinting leaves you gasping for air. This difference in physical toll is explained by power. While work measures the total energy transferred, power measures how fast that transfer happens. As this comparison shows, power is calculated by dividing work by time. Sprinting requires high power because you are doing the same work in less time. We measure this rate in watts. This elevator motor, for example, does 12,000 joules of work in 4.0 seconds. Dividing that work by time gives the motor a power output of 3,000 watts. We see this on household appliances, too. This microwave has a power rating of 800 watts. That rating determines how quickly it can do the 24,000 joules of work needed to heat your food, which in this case takes exactly 30 seconds. If work is the total volume of energy being delivered, power is the speed of the delivery truck. This flowchart illustrates the energy cycle. Energy is the capacity to act. Work is the mechanism of transfer, and power is the rate of transfer. This cycle governs every system we study, from a spinning wind turbine to the generator that lights a bulb. By defining a system boundary and calculating the relationship between force, distance, and time, we can account for every joule that moves through a system. It turns the complex motion of the world into a predictable, balanced ledger.